Okay, so now we're going to kind of switch gears from what we were talking about. Previously, we've been looking at more of kind of a review of Calc 3 or a generalization of this vector algebra to n-dimensional space, right? And we reviewed like dot product, cross product, a lot of these notions, because these are obviously very important when we're talking about vectors. Well, now that we've discussed all that, now we want to talk about kind of a collection of these vectors and what do we obtain or what can we get from a collection of these vectors. And so the first thing we want to start with is a spanning set. So let's understand kind of the intuition behind a spanning set here, or what one is really. So let's say we have two vectors, u and v. So let's say u here, and then maybe some other vector over here, v. Okay, and let's say these are, so we're actually looking in R2 here. So we can kind of imagine that we're just in the plane here with these two vectors. And you could take these arbitrary vectors and ask yourself, with like what subspace or how much subspace of the plane could I obtain just from linear combinations of these vectors, right? And so if you'll remember, a linear combination, let's use smaller. It's font here. So a linear combination is when a vector, let's say W, can be written as a sum of scalar multiples of these vectors. So a linear combination of the vectors u and v would be could be a vector W such that like a u plus b v equals W, right? We had this notion in general for an arbitrary number of vectors, right? We would say like maybe like W equals a1, sorry, a1 v1 plus et cetera, plus an vn, if you were looking at like a collection of n vectors here. And so the idea for a spanning set is to ask yourselves, or to ask the question, what is the set of all possible linear combinations of these two vectors can I get, right? And so what do we mean by subspace? Well, let's give a quick definition here. If you have, let's say U, capital U and capital V, let's let these be, or let's say W. So we have U and W here. Let's let these be sets of vectors in Rn. And then if every vector in U is also in W, then we say U is a subset of W. And we'll denote this with kind of, basically you can think about taking the union symbol, like the set union, like U union A and B, turn it on its side, and then we have this this little bar under it here. So what this means is that U, this would read U is contained in V, or U is a subset of V. Now, what we're asking is, given, so here's a question. Given a set of vectors, let's say, we can give it a name too. Let's call it U is the set of vectors v1, v2 through vk. We could ask ourselves, what is the set of all vectors obtained by linear combination of the vectors in U. Right, so here's this question. Let's say, for example, we were looking in R2, and we had the vector v1, which is 1, 0, and v2, which is the vector negative 1, 1. Right, you could look at the plane and say, okay, we have the vector 0, 1, v1, we have the vector v2. And now just taking linear combinations of these vectors, what could we obtain? All right, well, we could just start with something like v1 plus v2, right? If we took v1 plus v2, that would be the vector 0, 1. And so we know we could obtain this vector. We could take v1 minus v2 and get the vector, looks like 2, negative 1, right? Because you'd have 1 minus a negative 1, right? And then, so we'd have 2, negative 1, 1, 2, negative 1, right? You get something like this. And you could keep going, right? There's a lot of possibilities. And in this particular example, it turns out, and we'll see how to calculate this, it turns out that you can obtain any vector in the plane from just a linear combination of these two vectors. And so we want to kind of understand this formally, and we also want to understand how to calculate the span of a set of vectors. And so kind of our question rephrased now is, given this set of vectors, say v1 through vk, what we're asking is, what is the spanning set? We're asking, what is, and we'll denote it by the span of U, or we'll see this as span v1 through vk, like this. And so this is what we're asking here. We're trying to obtain subsets of n-dimensional space given a collection of vectors. So let's define this then. We've kind of defined it implicitly when we were asking a question. We were saying, what is the set of all possible vectors obtained by linear combinations of vectors in U, right? And well, then in the rephrase question, I've said, well, what is the span of U? And this turns out to be the definition. So the span or spanning set of U is the collection, or let's say set, because the spanning set is a set. The span of U is the set of all possible linear combinations of vectors in U, which is the set v1 through vk. And so this is what it means to be the spanning set for a collection of vectors. i.e., what we're asking ourselves here, or we could write this, if you'd like, since the span of U is a set, we could write it as a set. So in set notation, this would read span of U is the collection of all vectors W, and let's say we're in Rn, such that W is A1 V1 plus A2 V2 plus et cetera, et cetera. Sorry, I ran out of room. Plus AN VN, or let's say K, right? Because we don't necessarily have to have as many vectors as the dimension of our ambient space there. So basically the span is this collection of vectors such that W can be written as a linear combination of the vectors V1 through VK, which was the set U, right? And then here, to be more explicit, I should have written in the set notation, this is for A1 through AK. These are coefficients, right? They're real numbers or scalars. And so we would just say A1 through AK are elements of the reals there. And now that we know what a span is, kind of the set definition, like the set theoretic definition here, and also kind of the geometry of what's going on, right? We're literally looking for, if you'd like some intuition for why it's called the span, it's because we're looking for how far do these vectors span in space, right? Like, what is the limit of subspace that we can obtain just from these vectors, right? What do these things span? So now that we understand the geometric description and the set theoretic description here, let's look at an example of finding the span of a set of vectors. So let's consider the following vectors. Let's say we want to calculate the span of the vectors in R3, 1, 1, 0, and 3, 2, 0. And so we'll ask ourselves, what is the span of this set? Well, what do we notice? We notice what we're going to look at then is we're going to look at vectors W such that, and let's say A times 1, 1, 0 plus B times 3, 2, 0. We're trying to find the set of all vectors W such that they're written as something that you see on the right for constants A and B, right? And so as you vary the constants A and B, you're going to get different vectors, right? Like if you let A and B both be 1, then, so let's say if A equals 1 and B equals 1, well, then you're going to get the vector W, which is 4, 3, 0, right? And so we could say, well, the vector 4, 3, 0 is contained in the span of these vectors. And you could do that forever, right? But we want to be able to find a description for all of these vectors kind of concisely, right? We want to describe this as a set. And so one thing we notice is that the Z component of both of these vectors is 0. And because the Z component of both of these vectors is 0, we know W is necessarily going to be of the form X, Y, 0. Or we could also say, because we notice that both of those, the Z component there of our vectors is 0, we also know that the span, and let me just call this set of vectors just to save my life, or to save me some time here. Let's just call this set capital X. Why not? So the span of the set capital X, we now know is contained in R2, right? Because these vectors are going to have no third dimensional component here, right? And so we're just looking for vectors in R2. And then one thing you can observe is that now we're trying to relate these vectors. So we have like A times 1, 1, 0 plus B times 3, 2, 0. Excuse me. We're trying to find these coefficients A and B such that we get a vector of this form. Well, if you set A equal to negative 2x plus 3y, and B equal to x minus y, you'll notice that this just gives you x, y, 0. And the domain of A and B here, right? The domain means all possible x and y values that you can choose. This domain is R2, which tells us that the span of this set is identically R2 here. Okay, and so this is an example for being able to calculate the span. We'll see, you may ask, well, where did you come up with this, right? In the future, we'll see some techniques about how you can solve for the span in more complicated settings. For right now, we just kind of want to see some examples of what it is, right? But we'll, in the future, we'll discuss more about kind of where that came from, et cetera, et cetera. So now let's consider this example still with the vectors. Let's give them names. Let's say the vector 1, 1, 0 is the vector u, and the vector 3, 2, 0 is the vector v. And so here now, let's say we're trying to calculate the span of, well, it was 1, 1, 0, 3, 2, 0. And then let's say we're trying to calculate the span of, let's add another vector here. Let's add the vector 4, 5, 0. And we may ask, okay, well, now what's the span of this set of vectors, right? But you may notice that the span here, we still have a 0 in this third component, right? And since we still have a 0 in this third component for the new vector, and we know the span of these is at least R2, and we're not gaining anything from this third vector here, well, we know the span of this set is still going to be R2. And so there's this notion here of one of these vectors being kind of useless, right? Well, we added this vector to the collection of vectors, and we want to determine the spanning set, but it didn't change the span at all. This is a notion of linear dependence. Here, 4, 5, 0 is linearly dependent. And, or, you know, more commonly, you would say just this collection of vectors is linearly independent. And so again, if we call these u, v, and w here, we would say the collection u, v, w is linearly dependent. So this is an idea of what linear dependence means, right? It means that we can write one of the vectors as a linear combination of the other two. And we can see that almost right away. If we have 4, 5, 0 here, right? We would want to see if A times 1, 1, 0 plus B times 3, 2, 0, like we would want to see if this holds, right? We would ask ourselves, is W a linear combination of U and V? And you'd think it would be, right? Because the span of just the first two vectors here was already R2. And then we added this vector and it did not change the span, right? And since it didn't change the span, you could say, well, then it would make sense that that vector, which is a vector inside of R2, should then be in the span of the first two vectors, right? And so to see if it's in the span of the first two vectors, you have to ask yourself this question. Well, and again here, like what you would have to do to solve this, to answer this question, is you would have to go, okay, 4 equals A plus 3B, 5 equals A plus 2B. And then you would set up your augmented matrix. You'd have 1, 3, 1, 2, 4, 5, and then you would solve for A and B. If you do this, you can see that A would be 7 and B would be -1, which is to then say that W equals 7U minus V, which would then imply that 4, 5, 0 is in the span of, remember we were calling this X, like the spanning set before we included the vector W, right? And so this is in the spanning set of X. This is that notion of linear dependence here. It's like, well, we added this vector and it didn't do anything for us. So let's see if we can kind of formally define linear independence here. So let's give a definition. The set of vectors, let's say v1 through vk, is linearly dependent if you have a collection of 0 vectors here. So like a1 v1 plus a2 v2 plus et cetera, plus ak vk equals 0. And so what we're saying here is we have a linear combination of these vectors, but it gives us the 0 vector. So the set v1 through vk is linearly dependent if, when you find a linear combination that's the 0 vector, at least one of the coefficients ai is non-zero. Okay, and so why would this give us linearly or linear independent or linear dependence, excuse me? Well, let's understand here. So if we have a collection of vectors, or this linear combination of vectors, a1 v1 plus a2 v2 plus et cetera, and one of them is, at least one of them is non-zero. Well, if at least one of them is non-zero, that means we can divide through by it, right? And so we would get, let's assume, like without loss of generality, let's say a1 is the coefficient that's not 0, right? Just without loss of generality, we can choose that. And then so we would have v1 equals a2, oh, sorry, not equals, v1 plus, and now let's divide through everything by a1 because we know it's not 0. So we would have v1 plus a2 over a1, v2 plus et cetera, plus ak over a1, vk equals 0, right? And then this means that v1 is equal to negative a2 over a1, v2 minus et cetera, minus ak minus or over a1 vk. Well, then v1 then is all of a sudden a linear combination of these other vectors, which is exactly what it means to be linearly dependent, right? And so this is where that criteria comes from. And so if you have a collection of vectors and you can write a linear combination of these vectors that results in a 0 vector without every coefficient being 0, then you have a linearly dependent set. Let's look at an example. Let's say we have the following collection of vectors: 0, 1, -2, 1, 1, 0, -2, 3, 2, and 1, -2, 0. And we want to ask, is this linearly dependent? Well, to see if it's linearly dependent, we need to make a linear combination of these that gives the 0 vector without every coefficient being 0. And you can obtain this if you take one copy of 0, 1, -2 plus 0 times 1, 1, 0 plus 1 copy of -2, 3, 2 plus 2 copies of 1, -2, 0. If you do the arithmetic, you see that you get the 0 vector here. But in fact, only one of these coefficients is 0. And because that's the case, that means, yes, this set of vectors is linearly dependent, right? And what this means, so let's look at this example, right? If we algebraically, since we multiplied the second term by 0, we would think about that being eliminated, right? And then what you could do is rewrite the vector 0, 1, -2 over here as basically, if you'll excuse me here, I'm just going to kind of erase all of this. And then you would think about moving the 2 remaining vectors here on the right to the other side of the equation, right? You subtract them over, and you would get this is equal to, well, then all of a sudden you have minus here, and you have minus here. And so we found one vector, the vector 0, 1, -2, which is a linear combination of 2 other vectors within the same set. And so we say this is linearly dependent. Now, there's also a notion, excuse me, of linear independence. And so let's give a definition here. If, again, for a collection of vectors, let's consider V1 through Vk. If for any linear combo A1, V1 plus, et cetera, plus AK, Vk that results in the 0 vector, the only solution is A1 equals A2 equals equals AK equals 0, then the set V1 through Vk is linearly independent. Okay, and linear independence means all of these vectors are independent. None of them can be written as a linear combination of the others, right? Here, like for some intuition, here in this equation at the bottom of this example, here, the vector 0, 1, -2 is dependent upon the vectors -2, 3, 2, and 1, -2, 0. Here, that does not happen. If the only solution to this equation, or this system of equations, right? This is a system of equations here, because you get one equation for each component of the vectors. So this would be a system of inequations in k variables. If the only solution here is the trivial solution, meaning all of the coefficients have to be 0, then your set of vectors is linearly independent. And so how could one determine linear independence? Well, let's look at an example. Let's ask if the following set 1, 1, 0, 1, 0, 1, and 0, 1, 1, let's ask, is this set linearly independent? And so how do we know? Well, what we have to do is ask ourselves the following question. Is A times 1, 1, 0 plus B times 1, 0, 1 plus C times 0, 1, 1 equal to 0? Well, to be proper, this would be equal to 0, 0, 0. Are the only solutions to this system the solution ABC equals 0? How would we find that solution? Well, let's set up the augmented matrix corresponding to this system of equations, right? Because what is this following system of equations? This system of equations is A plus B equals 0, A plus C equals 0, and B plus C equals 0. The following augmented matrix is 1, 1, 0, 1, 0, 1, 0, 1, 1, 0, 0, 0, right? And so we need now we need to solve this system of equations by putting this augmented matrix in reduced row echelon form. You can see rather quickly that this gives you the following reduced row echelon form. I mean, you could switch row 2 and 3 if you'd like to get the 1 in the second spot, or you can just do, let's do this. Let's do row 2 equals row 1 minus row 2. For the sake of time, let's just say you get the idea, right? We're pretty good at reduced row echelon by now. So this goes to reduced row echelon form of 1, 0, 0, 0, 1, 0, 0, 0, 1, 0, 0, 0, right? Which means A equals 0, B equals 0, C equals 0. And so since this is the only solution we get that this set was in fact linearly independent. And so notice that kind of it was enough to just solve a system of equations to determine linear independence, although that wasn't in the definition, right? The definition just says if you have a bunch of zeros for coefficients, and that's the only possibility, then you're linearly independent. It didn't say if your solution to the corresponding system of equations is trivial, then your system is linearly independent. But that's the same thing, right? We've seen that's the same thing. And so there's a following theorem that kind of lists what all it means to be linearly independent. And so let's say the following statements are equivalent. The first one is that the set of vectors v1 through vk are linearly independent. The next one says that no vector is in the span of the others. And the third statement is that if we set the matrix A to be where each column vector, like the ith column, is the ith vector of our collection, so this would be like the column vector v1, v2 through vk, then the solution set AX equals 0 only has the trivial solution. And here, right, I'll kind of just be precise, X is your, X is just your like A, B, like your A1, B1 down to, or how about A1, A2 down to AN, right? This is what X is, and then solving that system, if it only yields the trivial solution, then that's the same as being linearly independent, which is also the same as saying that none of the vectors in this collection are in the span of the others, right? Okay. So there are a few more theorems that I would like to mention here. And right, we've done an example now to see if a set of vectors is linearly independent. What you always do is you take your collection of vectors, you set up the matrix of these vectors, right, where each vector in your collection is a column in the augmented matrix. you set it equal to 0, and then you put that augmented matrix in reduced row echelon form to see if you get the trivial solution or not. If you get only the trivial solution, then it's linearly independent. If you get anything else, then it is not, right? And so we've seen an example. Now let's see some theorems or some properties here. So if we have that U is a set of linearly independent vectors, then for every x, right, for all x that's contained in U, x can be expressed as a unique linear combo of vectors in U. And this is important, the unique aspect, right? And so if you have a set of linearly independent vectors, every vector in the span has a unique representation. That's exactly what this theorem is saying. We have another theorem that says, let's let A be an n by n invertible matrix. And what does invertible mean, right? It means A inverse exists. Or it means the determinant is non-singular, right? So then the column vectors of A are linearly independent and span the entire ambient space. They span Rn. Okay? And so that's what, for an invertible matrix, basically, we'll learn the notation in the next video. But basically, if you have an n by n invertible matrix, then the column vectors of that matrix define a basis for Rn, okay? Which means they're linearly independent and they span Rn. We also have row vectors of A are linearly independent and span the set of all 1 by n vectors, which this can still be thought of as Rn, right? Because what's a 1 by n vector? Well, that's a quantity with n entries, right? You can put n numbers into it. Well, and if it's all 1 by n vectors, well, then that's Rn, right? But we really think about Rn being the span of the column vectors, and then the row vectors just being 1 by n vectors here. Okay, so I think that's all I would like to talk about for now with spanning sets, linear independence. We'll see them a lot more, and these notions can be kind of confusing at first. So hopefully after doing some examples in the video, and then after you'll do plenty of examples on the homework, I'm hopeful that you'll get a much better idea and intuition for what the spanning set's doing, what linear independence means, what does it mean to be linear dependent, et cetera, et cetera. And once we start to talk about like bases and subspaces in the next video, we'll use these notions that will hopefully make things a little more clear.